Mike Lavin, this is Sasha Filius and Janssen Rosenberg, and together we are developing an in-situ manufacturing method for LTCC-based microchannel heat exchangers. So I'm going to give the floor over to Sasha, who's going to be going into our motivation and manufacturing background.
So in the future, NASA will have a need for self-sufficient space stations. This can be accomplished with ceramics and additive manufacturing by utilizing the natural soil of the moon and different planets. Ceramic manufacturing is a proven technology to be used to create complex devices. The manufacturing process itself will be simple and easily duplicated in space with just a few minor modifications. Additionally, space material has a composition of ceramic and glass that makes manufacturing feasible. The first portion of this project is to create a ceramic heat exchanger using DuPont's LTCC 951 tape. That will be accomplished by punching vias, cutting fins, stacking the sheets, laminating, and firing them. At the same time, we'll also be doing the material characterization of the Martian and lunar regolith. We'll be using ball milling, pellet pressing, and sintering studies performed at different temperatures in order to characterize the materials. Once that's done, we'll be able to formulate a regolith-based tape, and it will follow the same procedure as the LTCC process in order to create a regolith-based ceramic, regolith-based heat exchanger. The 951 LTCC tape and the simulant have a very similar ceramic composition, and if we're able to produce a heat exchanger with the LTCC, then it demonstrates the feasibility of creating regolith-based devices for the future. Basically, this project can be produced anywhere on Earth that has soil. So we'll be using different soil configurations in order to demonstrate the global applications of the process. And the process itself will be an important step in eliminating some of the physical limitations of space exploration.
All right, so our particular application is going to be a microchannel heat exchanger. We're going to be using Murray's Law in conjunction with fins made out of silver, constructed in an elaborate pattern in order to produce a higher heat exchange density. This is our initial test design. As you can see, it's a single pass heat exchanger. It has a main channel that's 5 millimeters by half a millimeter, which breaks down into 7 subchannels according to Murray's Law that are each half a millimeter by half a millimeter. The purpose behind this was just to prove feasibility, demonstrate performance, and give the manufacturing equipment in the materials lab the geometry file to work with. Now, globally, there's actually been large growth in microchannel heat exchangers. Most of these devices, however, are being built with aluminum. Not so many of you using LTCC. However, with that being said, we did track down a group in Brazil that's using LTCC, as well as our own Ari, who's in the mechanical engineering department. And both of these individuals were using LTCC tape to produce microchannel heat exchangers. All right, so now that the manufacturing process and the application have been described, these are the general overview of the flow of the work that's going to be produced. Essentially, we have multiple processes that are being conducted in parallel. For the manufacturing side, we're using the commercial 951 tape to produce a heat exchanger, as well as simulant tape that's being produced and ultimately, as Sasha said, is going to be used to produce a heat exchanger in the same fashion that the LTCC tape was. We're also going to be producing an optimized design through optimization software through ANSYS and Mode Frontier. And currently our progress sits at, for the materials characterization, we've got the lunar regolith ball milled down to 3 microns. We've pellet pressed that material and fired at multiple temperatures and done XRD and SEM analysis, although the SEM analysis is somewhat inconclusive due to one of the detectors in the SEM being a little malfunctioning. For the commercial device, we've actually produced our initial test design that we showed in the previous slides. And we've produced an initial CAD model and initial simulation studies to determine performance.
These are the major milestones for our project. The lunar regolith characterization is already complete ahead of schedule. We'll have both soils characterized by June 20th with simulant sheets created by July 18th and an initial build by August 1st and an optimized heat exchanger by October 10th. Here are the materials and costs for our project. We're at $4,183 total cost. For the final goals, by the end of the project, we'll have a method for lunar and Martian regolith characterization that can be extended to other soils with similar characteristics. We'll have a method for manufacturing products with using almost exclusively extraterrestrial materials. We'll have an optimized heat exchanger that will maximize heat flux while simultaneously minimizing pressure drops across the heat exchanger, and will be hermetically sealed. If time allows, we will work with NScript to couple our single-inch inks with their 3D print technology and to use direct print additive manufacturing, and this will be the foundation for in-situ manufacturing.
Thank you, everybody.
Thank you. All right, any questions? Yes, Dr.
Question. If you go back to the very beginning, explain to me, you're trying to exchange heat between what and what?
Okay, this is our initial design. Essentially what it is that top white portion.
Would you use a pointer?
Use a pointer.
Oh, yes, sorry.
Closer to.
Okay, right there. This is essentially a conducting pad. What we're going to do is we're going to put a processor or some type of electronic device that generates heat onto this pad, and hopefully it will conduct through the pad, down in through these vias, into fins, and there's going to be water flowing or fluid flowing through these channels, and that channel, and that's going to allow for convection of the heat to be removed from the system.
And where are you going to dissipate this heat?
We haven't thought about that yet.
Well, it's
It's definitely something to think about.
It's pretty interesting.
Right now,
This is,
we're in the.
Let me finish my question.
Okay, sorry about that.
Where are you going to dissipate the heat? The question is, I'm going to substantiate the question. You're talking about extraterrestrial. Many planets don't have atmosphere. How are you going to dissipate this heat? If they have atmosphere, some of them are hot like hell, much hotter than this. How are you going to reject this heat into such an atmosphere? What are you going to do? The three modes of heat transfer: conduction, convection, radiation. You count strictly on radiation, you dissipate the heat once it gets out. Did you give it any thought?
That aspect, no. But we, kind of
Think
just
about
thought
it.
it was
Think
going to
about
work the same way heat convection works on planet Earth.
Because it has to fit into something realistic.
Yes.
Second question, you're talking about some material which is ceramic rather than metallic.
Yes.
What's the reason?
Well, the ceramic material is just the housing for the actual framework. The heat transfer is all going to be done through a silver medium. Everything
I'm not
you see
following
here
this
that's in
at all.
white.
I'm
What's
not
that?
following this answer at all. In this here sketch,
Yes.
what is metallic, what is ceramic?
This is the silver, so everything that's this color, including the fins and vias, this is all silver. So this is where all the conduction and convection is going to occur. Everything else, the housing, is all through LTCC, which is a ceramic-based product.
So the vertical struts between the fluid flow passages are ceramic.
No, those are made out of silver.
That's what I want to know. So it's not just the surface pad on top, it's metallic. It's also
Yeah.
vertical walls which are metallic, right?
Yes.
Okay.
The vias and the fins, as well as the conducting pad, are all metallic.
Okay.
Why don't you go back to that drawing of the one that we built 10 years ago? Which has the columns. No, well, you can't really see it. When we had our diagram, that's built
I
up
would rather have a team give the answer and present
Okay.
this.
Yep.
So if you don't mind. So guys, I cannot read any of you guys. I had to completely read that. My eyes are not good. Even with glasses, I cannot read this. So I'll have to ask the question because I cannot read what you wrote back. The question is, what is the level of heat flux that you are going to anticipate?
Right now, we're just looking at that initial CAD model that you saw in the simulation study. That was just with 5 watts being conducted through the plate.
What, about 5 watts per square
No,
centimeter?
5 watts total energy.
Per-
The area was, I believe the conducting plate was 5 by 12 millimeters.
Heat flux is a given per unit area.
Yeah, it was about 66,000 watts per meter square, about.
Okay. Thank you.
Any
All
other
right.
questions?
Any other questions? Dr. Basilville?
I forgot.
One minute.
Well,
Somebody else.
go ahead,
I
Dr.
just
Dr.
one little
Jones.
bit, because I don't want to interrupt the meeting, but this is in response to a NASA SBIR that we responded to. And NASA's doing a big push to try and build things, and one of the things they wanted to build was a cross-flow heat exchanger.
So this is NASA funded?
We will find out on the 27th.
Oh,
If not, they're going to have a. It's gonna be a more complicated project. So,
Well put.
All right, any other questions? Dr. Kim?
Really, the only question I was going to drop there was, you made a statement that all of the source of the materials would be in space, and then you tell me that the conductor is silver. Is there a silver source sitting on the moon?
That was probably misspoken, that there are going to be some materials that are going to be transferred over from planet Earth. The goal was to minimize the need for Earth-based materials. So it would mostly be the ceramics that are being produced in situ, whereas we would be pulling some precious metals and whatnot from the planet Earth. But if you can see from the volume of the two, the actual metallization is significantly less than the ceramic portion.
Dr. Basil?
I can't remember.
You got no more?
Any questions?
All right, that's it, thank you so much.